Hey, good afternoon or good morning. Today we're going to be continuing our lecture involving chromatography. This is the second lecture in this topic. And this PowerPoint that I have posted will be supplemented by the video that I'm currently doing. Just a reminder, some deadlines. The sapling homework assignment 6 is due on Thursday, April 16th. I've also posted a 7th assignment that's due on Monday, April 20th, which is the last day of the semester. It'll involve the final homework assignment, separations and chromatography, the topic that we'll be spending most of the time on today. Reminder, exam 3 is going to be administered through sapling, and it's set up for 1 hour. It'll be on Friday, April 17th, and topics will involve EDTA titrations, UV vis, absorbance, electrochemistry, and extractions, chromatography, the final topics that we're going over. Just remember, when you start the exam on sapling, you'll have a time frame to complete it. You can't stop and restart, so make sure that you're prepared to take the exam. There's no leaving, starting over again. Make sure that you're ready to go when the exam starts. It ends after the time interval's over and it shuts down. Just a brief look at the future. Final exam is also going to be administered through sapling, and it'll be on Friday, April 24th. And I'll have that open from 10:30 a.m. till 12:30 p.m. The 2-hour time frame. It's cumulative. It'll be worth 100 points. And like this exam, you can't stop and start. So be prepared. It's my exam. I'm writing it. It's not an ACS standardized exam. So that's important to know. So today, I'm going to pick up and begin with something I wanted to let everybody ask. And someone did send me an email, and they asked me to do a specific question. So in our final few lectures, we got like 3 more after today. If you want to send me an email or discussion posts on Canvas involving a question that you have on a problem, send it to me and I'll do it as a review before our lecture in the video format. Now, what I don't want you to say, Dr. Patton, do sapling problem such and such. No, I want you to find a problem that's similar to it. You can find one in your textbook. I will not do problems directly from sapling. Make sure you understand that right now. Look up a problem that's similar, and I'll do that for you to help you on sapling problems. I will not do sapling problems word for word, just as a hint. So this is a problem that I posted on an earlier lecture PowerPoint. And we did this one probably through a video, I think. Let's read the question and let's find out how we can answer it. Someone asked me this. So this is a review. A standard that has a concentration of 3.15 times 10 to the negative 6th molar. If you can't see it, I'll write that down again. 3.15 times 10 to the negative 6th molar. That's our sample, the concentration of it. And we're just going to call this compound X. And what we do is we go in and we conduct an experiment. We're using UV vis absorbance for this example. And we measure its transmittance of 54.11% at 635 nanometers in a 1 centimeter cell. So this would be a cuvette. And then we conduct another experiment on a blank solution. We could do these in either order. I can measure my blank first. I can measure my unknown first, my standard in this case. The blank solution had a measured transmittance of 95.78%. And it's conducted in the same 1 centimeter cell. Question is, what's the molar absorptivity of compound X at 635 nanometers? So think about the problem. I'm going to let you think about it for a minute and erase this if you want to write it down. And we're going to go through a strategy and think about what we're doing in this experiment, because this is really similar to what we would do in the laboratory. So let's think of how we're going to solve this problem. As I erase it, think about it. You can work on it. So I'm going to leave some information up here. This is our standard, or our standards concentration. There's the percent transmittance of our standard. And let's just remember that our blank was 95.78%. I'll just call that 95.78% T. What do we do? Okay, what we're doing in this example, if you're wondering, we're simply going to use Beer's law to help us solve this problem. Remember from Beer's law tells us that the absorbance of a sample, and in this case it's sample X, is equal to the product of the molar absorptivity of that sample multiplied by the cell length, and we'll call that B, and concentration. Now, remember, absorbance is directly proportional to concentration. And normally, if we conduct an experiment involving a series of standards, we create a calibration plot. And if the concentration is in molar units, then the slope of that line is going to be our molar absorptivity. So that's something we could do experimentally. Well, in this case, we only have one sample. So what we're going to do is we're going to use the concentration of our standard and the absorbance of the standard, the corrected absorbance, to rearrange this and solve for the molar absorptivity. So when we're giving you information about a sample and a blank, we normally, or we will, use a corrected absorbance. So let's think about the absorbance of X. The absorbance of X, as you recall, is, if we know the transmittance, the absorbance is the negative log of the percent transmittance divided by 100. So this will tell us what the absorbance of X is. So if we take the negative log of 54.11 divided by 100, this is 0.2667. Let's also calculate the absorbance of our blank. The absorbance of the blank is the negative log of 95.78 divided by 100. And that's going to be a pretty small value. I get 0.0187. Now, remember what we're doing in this experiment. We take a blank sample and we measure its percent transmittance in an instrument, and it reads back the absorbance, such as most of these instruments are set to do. Now, what the absorbance of the blank tells us is that if there's any imperfections in the sample holder, or if any of the reagents that we're using to prepare our sample absorb, if we subtract the absorbance of our blank from the absorbance of the sample that we're interested in, we correct for any of those errors that would lead to a wrong value in the absorbance for our sample. So we're simply going to subtract the absorbance of the blank from our standard. So that's important. We subtract the absorbance. So if we take the absorbance of our blank and subtract it from our original sample, we get an absorbance of 0.248. Okay, so that's the absorbance of our sample. The corrected absorbance and we'll just put a superscript on that. That's our corrected absorbance. And that's actually better to use. We would use, if we have a blank and we use it, the corrected absorbance is what we're going to be using for any kind of quantitative information. So now that we know that, we've calculated it here, we're going to use that information in Beer's law. We're going to take our corrected absorbance, its knowledge, and we're going to determine the molar absorptivity by plugging in all the information that we have. It's a 1 centimeter cell, that's B. The concentration, now remember, absorbance is a unitless number. Sometimes we use AU, absorbance units, but it's really a unitless number. If we solve for the molar absorptivity by taking these two and dividing them on 2.248, the molar absorptivity for our sample is pretty big. These are usually pretty big numbers for samples that absorb well. This is going to be 7.87 times 10 to the fourth, and it has units, inverse molarity, inverse centimeters, and that's the molar absorptivity of our standard X, our sample. Now, this would be important information at this wavelength that tells us what the molar absorptivity of our sample is. Now, if we were doing an unknown, we could use that molar absorptivity of the sample at that wavelength to do our experiments. So that's an example that I did in an earlier class, and I think there may have been a problem like that on sapling if anybody is working on that problem. So that's our review. If you have more questions like that, we'll do them before our lecture. Now we're going to do a lecture. So today's lecture is going to continue in chromatography, the process of separating components from a complex mixture. We can have two components, we can have multiple components, but oftentimes the issue is one of these components might be interfering with the measurement that we're making. Or we might simply just want to purify and isolate a compound of interest. So the topics that we're going to cover today are in Harvey chapter 12 and in Harris chapter 22. And we're going to pick up where we ended our last lecture, and that's discussing a little bit about why bands, chromatograms, the peaks that we see in a chromatogram, why do they broaden? And what we're going to also introduce is a theoretical model to explain how we can use information from a chromatogram to determine if our separation strategy is efficient. Or we can also use the parameters of our instrument to learn about the efficiency of the process. The main parameter that we're going to look at is column length in our first few examples. So let's recall what happens when we put a sample onto a column and we start to separate it. And we're just going to look at a single sample to begin with. We're just going to look at one component. How's that? A single component, perhaps in a mixture. Now, if we had a column, and I think it's better to draw it in this direction. Remember, our columns, normally we think of them as going from top to bottom, but we're looking at this in terms of time along the column. Here's our column. I'm going to get a better marker. These markers are not too dark. Let's try a blue one. How's this one look? That's not much better. There's our column. Mix it up, make it black and blue. Okay, there's our column. Hopefully we can all see that. There's our column. And what we're going to do on this column is we're going to put some sample at the very beginning, at the inlet. So this is where we're putting our sample. We're going to load a sample. Got that written in red letters. We load our sample at the beginning of the column. And what we would recognize is as the sample moves along the column at a later time, and if we looked at that particular sample at that time, we may notice when we measured our chromatogram, we would get a pretty sharp peak. And that's what we like. We like peaks that are pretty symmetric, Gaussian, and in this case, it's not too broad. What happens if we let this sample go down the column further? Well, what happens is later on, notice the peak height might drop down a little bit, but the big thing is it starts to broaden out. Now, what we should recognize is that the concentration of the sample is proportional to the area of the peak. So even though it becomes smaller, it gets broader and it has the same area. And this is known as peak broadening. If we looked later at our column, like way down here, that's what we might see, a very broad peak. And that's not what we want when we do chromatography. We like things to be fairly narrow. Now, there's two factors that we ended our last lecture. I probably mentioned one, but there's actually two. There's two main reasons why bands broaden, and they are interrelated. These two factors that are really influential. Diffusion. Diffusion's really important, and we're going to spend some time discussing diffusion. And time itself. These are two big factors, diffusion and how long that analyte spends on the column. Those two factors influence the peak broadening that we try to minimize. So if you haven't had a class that discussed diffusion, material transport, we need to understand a little bit about that. So let's define what diffusion is to help us understand this process. So diffusion, a lot of us may have had experience with the definition of diffusion, but for those who haven't, we can define diffusion Diffusion is the net transport of solute from a region of higher concentration to lower concentration. So that's basically what diffusion is. What happens when we have a solute in a band? Well, diffusion, it starts diffusing in lots of different positions. Brownian motion, small particles randomly move around. Diffusion causes this band, one of the reasons that cause band broadening. Now, the rate at which a solute particle moves is reflected in what we call a diffusion coefficient. Diffusion coefficient is given a capital letter D. And we have tables that list diffusion coefficients. The diffusion coefficient has units of meters squared or distance squared per time unit. It could be meters, it could be millimeters, it could be micrometers. Now, it's essentially a measurement of rate at which solute particles diffuse over a region in which there's a concentration gradient that causes diffusion. Now, the diffusion coefficient in this effect of diffusion depends primarily on two factors itself: the nature of the solute, size, and the nature of the solvent. If you look at today's PowerPoint, I gave a table that shows some different diffusion coefficients for different analyte species. Now, there are two that I sort of mentioned in the PowerPoint that I think would really give us a lot of detail about what's going on. Serum albumin, if you look at the table, serum albumin. Now, this is a pretty big biological molecule, serum albumin. It gave you the, I think it gives you the molar mass of it, pretty big guy, and its diffusion coefficient is pretty large also, or pretty small, I'm sorry. It has a very small diffusion coefficient, and if we compare serum albumin with a smaller molecule, that's methanol, we would see that methanol diffuses a lot faster than serum albumin, and the reason is methanol is a heck of a lot smaller than this big biological species. Smaller substances, smaller particles diffuse more effectively, and they have larger diffusion coefficients. So size, very important in determining diffusion properties of a particular analyte. Another property is the nature of our solvent. The nature of the environment. What we're looking at, the environment in which this particle is placed in. If we think about liquids and gases, particles in the gas phase, well, they diffuse pretty effectively. Substances in gases are going to have they diffuse more than liquid phase. And it's simply because gases don't have any types of intermolecular forces, or normally we neglect them. Liquids have intermolecular forces associated with them. I ask you to look at oxygen in this table. Oxygen's in air. It has a diffusion for gases about 10 to the 4th times greater than substances that are in the liquid phase. So the nature of the solvent is also very important when we start to think about the effects of diffusion on our environment that we're working with in terms of chromatography. Because we are going to, at the end of this section, compare and contrast some differences and similarities between liquid chromatography and gas phase chromatography. This diffusion effect is going to be really important when we start that discussion. So let's discuss now about peak broadening, because we said diffusion and time are two features that affect the broadening of a chromatographic peak, or we sometimes use the word band. So normally what we like to think about, we like to think of these chromatograms as ideal Gaussian peaks. And that's what we're going to focus on. Let's just draw a little axes here. And let's draw an ideal chromatogram. It's Gaussian, it's symmetric. That's what's really important about this ideal, because oftentimes when we conduct an experiment, we might get non-symmetric peaks. But we're just going to focus on the symmetric ones to make our lives a little. There's a peak that we have right there. It's Gaussian, and it's symmetric. And if you recall from probably the beginning of the semester, and we discussed a little bit about Gaussian distributions of data, we introduced the standard deviation. Now, if we look at this peak right here, and we defined its width, The width of a Gaussian distribution is defined by its standard deviation, sigma. I'm going to try to find a marker that works. That one's not too good. Let's stick with the purple one. Purple one's good. Sigma. Sigma, remember, is reflective of the width of a Gaussian distribution about half of its peak height. Now, this broadening would tell us that if we have a broadening of a chromatographic peak, the standard deviation is going to increase. And there are two factors that we want to understand a little bit about that affect this, and that's diffusion and time. And what we want to do is show how our standard deviation is related to it. We could go through the derivation. And what we see is that the standard deviation of a Gaussian peak for our chromatogram is dependent upon both diffusion coefficient D and T, which is the time that a solute spends on a column. So those are two important features that tell us a little bit something about the width of a peak. Remember, the more a solute diffuses, the more it's going to move away from the center. The longer a substance stays on the column, as we showed in that last example, over time, we get this broadening effect also. Now, from this definition of our standard deviation and its relationship between diffusion and time, we can relate and we're going to show a little bit of how we can derive an important parameter that's used to discuss column efficiency. HETP. Let's define what that term is. HETP is height equivalence. We'll define each of these. Height equivalence of a theoretical plate. Now, this is really important parameter that we use to discuss the efficiency of a column. If we look at our expression here, sigma is equal to the square root of 2 times the diffusion coefficient multiplied by time. We can go through and explain this a little more by deriving this. And what we would get is we would get a definition of our plate height, and we call that H. Plate height is simply equal to 2 times the diffusion coefficient divided by, now UX, now remember we'll define those, D is our diffusion coefficient. So the more we diffuse, the larger our plate's going to be. UX is defined as the linear flow rate, and that would be the flow rate of our mobile phase. Linear flow rate is defined in terms of a distance over a time. It's a speed. It's a rate of how fast our flow is going. So important here, and we're going to go through this a little bit more when we introduce another equation later called the Van Demeter equation. But what's really important about this discussion today is plate height, the height equivalence of a theoretical plate. So this brief derivation of what H is really at the heart of plate theory in discussing column efficiency. Now, I'm going to go and draw a little picture of what plate theory is. Sometimes it's kind of hard to imagine it. But let's discuss a little bit about plate theory, because the height equivalence of a theoretical plate, very important. Remember, when diffusion is big, the height of a plate is going to be large. Let's remember that for a few minutes. So I'll leave that up there. And we're going to go in a little exercise on what plate theory it really is at the heart of, what it means and who derived it. Now, plate theory itself is simply a model that we use to think about what's happening in a column where we're having a separation occur. And this theory was developed by two scientists that worked together. They collaborated, Martin and Singe. They use this model to help us understand a little bit about column efficiency. And it's going to allow us to use our parameters of the chromatogram and the instrument itself to help us understand if we can make improvements in our strategy. So this is the heart of what we call plate theory. Plate theory. So as the name implies, there's going to be some plates involved. So now plate theory, what Martin did, and Martin was doing this probably in the 1930s or 20s, and this theory came out in the 1940s. They were dealing a lot with distillation. Now, what happens in distillation, if you've ever done any kind of distilling, making your own booze maybe. Now, distillation is the process of transferring a substance from its liquid phase to its gas phase. And in many cases, it's going to go back to its liquid phase. And this would be how we would purify an alcohol from water if it was in a mixture. So we use differences in boiling points. So what we use plate theory, it's helping us understand about the equilibrium that's occurring in a column. So let's draw our column again and understand a little bit about plate theory. Here's a column, and we're going to look at it downward now. And what we think of in plate theory is that the column itself is separated into theoretical plates. Again, it's theoretical. And let's think of this as one plate here. And we'll draw a line and put up a little coloring in there to help us see it. And then there's another plate below it. We'll use red so we can see that with our eye. And we'll use some color there. And then there's another plate below that. And we'll put some coloring, that's green. And then there's another plate below that. So are we starting to get an idea? Hopefully it'll make sense in a minute. And this would go on, and we would have a lot of plates. And what's happening within each of these plates, these are called our theoretical plates, there's an equilibration occurring in which solute is equilibrating from mobile to stationary phase, just like we showed in extractions. So each of these plates represent an equilibrium event from solid to stationary back to, or from mobile to stationary back to mobile. It moves a little further. It goes back from mobile to stationary back to mobile, and it moves a little further, and so on. And we get a series of these plates that represent each of these equilibration events. So that's the gist of what plate theory is getting at. A lot more detail. If you took a grad course in this, you'd probably go and spend like a couple weeks discussing it. So for our case, plate theory is simply a model to help us understand about how we can make improvements in our column. So what do we desire when we think of plate theory? So my big question, what do we desire? This is why I left this up here, this equation. Remember what we said. We like peaks to be pretty narrow. And when we get a lot of diffusion, they broaden out. And guess what? When we get a large factor of diffusion, our plate heights get larger. So what we desire a small plate height, a small h, And we're going to introduce another number here, and that's the number of plates. N is the number of plates. So if we have a column of a certain length, and we're comparing it to another column that has the same length, we would want the column with the smaller size of the different plates would give us a greater number of plates. So what we want is, we want a small plate height and a large number of those plates over a certain length of column. So the number of plates that we desire is large. So when we have a small plate height, we can get a lot of these equilibration events occurring. And that tells us that we have a large number of plates in our column. And guess what? We're going to get better separation when we meet these two requirements of our column. So these are important because those can tell us a little bit something about how we can control our conditions to give us better efficiency. And we have equations that represent the number of plates and plate height and how they're related. And we're going to be using these equations when we look at a chromatogram or our experimental conditions. So plate theory, let's get rid of that. I think we don't need that anymore. We don't need that. We have equations that relate the number of theoretical plates. We'll call that N, and we'll define that. The number of theoretical plates. And remember, our goal is to get a large number of theoretical plates. We like this to be big. It equals L. L is our column length. Divided by H. H, remember, is our height equivalence of a theoretical plate. HETP. And we like this to be small. If H is small and it's in the denominator, we get a greater number of theoretical plates. And if we're comparing two columns that are the same length, the column that has the smaller plate height would give us the greater number of theoretical plates, and that's going to give us a more efficient separation strategy. So that's important for discussing parameters related to column length, plate height, and the number of theoretical plates. So I know you're looking at that and you're like, okay, I can probably go in and measure that. I can find out what my column length is, maybe from the package that the column's in, or simply go in and measure, if it's a glass tube, how long it is. But how the heck am I going to find this out? Or how the heck am I going to find that out? Looks like I have two things that are kind of obscure or abstract with something that's pretty solid that I can go in and measure. So we need something to tell us more, to give us better information. And that's another relationship for our theoretical plate number, N. Remember, N is the number of theoretical plates. We use our chromatogram to tell us what that is. And the parameters from a chromatogram are really important. N is equivalent to 16 times TR squared over W squared. Or if you would like, it's just 16 times TR over W, and we square that ratio. Now remember what these two are. These are parameters that we get from our chromatogram. TR is the retention time of our species. So let's look at a chromatogram. Can you see that? That's good. You can see that. And we're measuring time. And we have our signal from our response. And we get a peak right there. And if we were measuring this from the time of injection, TR is the retention time for that species. W. W is defined as the baseline width of that peak. There's our baseline width right there. Okay, we also have another way to measure this, because here's the issue that we have sometimes. Sometimes it's difficult to measure baseline width. It can be. It can be kind of a drag, kind of hard, especially when we get asymmetric peaks. We can also relate this to another feature that we measure a lot. And we're going to call this the width at half height. A little easier to measure the width at half height in many cases in comparison to the width at the base of the peak. So the way we can express n, if we're using this as our measurement, width at 1/2, we define n 5.55 multiplied by our retention time squared divided by the width at half squared. And if you did some geometry, you could probably derive how we got from here to there based upon that peak at half height. And I gave you these equations all on today's PowerPoint slide. So we use this type of information to make decisions about if our chromatographic process and the separation strategy is giving us the required number of theoretical plates, or our plate height is meeting a certain requirement that we want to give us our separation. Let's go through an example of how we would use this information. And again, these equations are plug and chug. They're really not that hard of problems. You just simply need to know which equation to use. So this is an example from today's PowerPoint of using this information in this equation right here. So I'm going to erase this because it's right in the middle of the board. And if you look at today's PowerPoint, I have the equation written there. And we're going to look at the chromatographic analysis for a pesticide, something we might be doing in the real world if we're working in an environmental application. So this is our example for today. So if you're reading through this example, we're doing a chromatographic analysis for a chlorinated pesticide. And this pesticide's name, dieldrin. Wow. They even have names that sound kind of intimidating. First three letters are di. Probably not going to want to eat that, right? So that's not too good for us, I would think. It gives us a peak with a retention time, TR, of 8.68 minutes. And it gives us a baseline width, not the width at half height. This one gave us a baseline width of 0.29 minutes. So what's real important about these problems is that your retention time and your widths have to be in the same units. Usually it's going to be a time unit, Then you got to watch out for if the width is given in seconds and the retention time is in minutes. You need to convert one of them so that both of them are in the same unit, whatever one you decide. So make sure you know that. Let's calculate the number of theoretical plates. N is 16. From the information that we're given, we can use this equation. If we plug those numbers in there, we get 16 times 8.68 divided by 0.29. And these are both in minutes, so nicely cancel out. We get a number of plates, 14,334 plates. Now, this is a nice number, it's pretty good, but it's only useful if we can compare it with another situation. What if I said we did another separation using the same compound and we got a retention time of such and such and a baseline peak width of such and such? Which one gave us better separation? We can compare their value for N to tell us a little bit about which one is more effective at separating or having this sample come off a column. We're going to use this a little bit later, this information, in determining resolution between two species. But for now, we need to know how to do this before we move any further. One other question I asked on this problem, if we told you the column had a length of 2 meters, pretty big, pretty long column, 2 meter column, 2 meters, that's 6 feet. 2 meter column had a length of 2 meters. What's the plate height? What's HETP? That's our plate height. Remember, since N is equal to L over H, we can rearrange this. H is equal to L divided by N. If L is 2 meters and N is 14,334 plates, then the plate height, HETP, the height equivalency of a theoretical plate, 0.14 millimeters. I've converted that into millimeters. And that's how we use this information to give us information either about the number of theoretical plates that we have or the height of an individual plate. We're going to be using this information in more detail on Wednesday when we discuss how we can use these parameters to compare the resolution of 2 or more species that's coming off a column. Thank you. Have a nice day. Send me questions.